So now we're going to look at how we can determine the standard cell potential, okay, if we've been given two specific half cells that are connected to each other, okay, under standard conditions. So let's say that I have a zinc half cell, right, Zn2 plus Zn half cell, and which is connected to a copper 2 plus copper half cell, okay, and I want to determine the standard cell potential. That is the EMF of the cell, right, the electromotive force or the voltage of the cell when these two half cells are connected to each other, okay. And again, obviously we're using 1 mole per dm cube solutions of zinc 2 plus and copper 2 plus, right, 298 Kelvin and 1 atmospheric pressure, because we're talking about standard conditions. Now over here, right, if you look at the data booklet, right, we have the following two half equations, right. We have the standard reduction potential of zinc, or the standard electrode potential of zinc, right, from the data booklet, right, and that is negative 0.76 volts, okay. And we also have the standard reduction potential of copper 2 plus, right, to form copper metal. Again, this is from the data booklet, right, and this value is positive 0.34 volts. Over here, we can say that based on the standard reduction potentials, remember the standard reduction potentials are a measure of oxidizing strength or strength as oxidizing agents. We can say that copper 2 plus is a better oxidizing agent than Zn2 plus. It undergoes reduction more readily, it has a more positive standard electrode potential, right? So we can say that copper 2 plus will undergo reduction, right? Copper 2 plus will undergo reduction. And we can also say, looking at the reverse, right, we can say that zinc is the better reducing agent. It undergoes oxidation more readily. It's a more reactive metal. So we can say that over here zinc will undergo oxidation, right? It is the reducing agent. Okay. So zinc will undergo oxidation. So here we have our two half equations. So over here we can say that the copper electrode is the cathode, right? The copper electrode is the cathode, right? That's where reduction is taking place, right? And the zinc electrode is the anode, right? That's where oxidation is taking place. And since electrons are flowing from zinc to copper, we can say that the anode here, the zinc electrode, is the negative electrode, right? It's the negative terminal, right? This half cell, and then the copper half cell is the positive terminal, right? So these are two half equations for the cathode and the anode, right? Now, what is the electrode potential for the cathode? The electrode potential for the cathode is positive 0.34 volts, right? And what is the electrode potential for the anode? This one is reversed, right? The standard reduction potential of zinc is negative 0.76. Here we're talking about the oxidation of zinc, so we're looking at the reverse reaction. So this will be positive 0.76 volts. So then what is the overall EMF of the cell? The overall EMF of the cell, or the EMF of the cell, right? That's your standard cell potential, is positive 1.10 volts. And if we were to look at the overall equation, right, we have the overall equation here is copper 2 plus reacts with zinc, right, to form Zn2 plus and copper. You can also simply use this expression to determine the EMF of a cell. Okay, the EMF of a cell, okay, this is the EMF of the cell, or the standard cell potential, is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. Okay, the standard reduction potential of the cathode minus the standard reduction potential of the anode. So again, these are your standard reduction potentials. Okay, these are your standard reduction potentials. Okay, standard reduction potentials. So here, if you look at the two half equations, right, the standard reduction potential for zinc is negative 0.76. The standard reduction potential for copper is plus 0.34. Our cathode is the copper 2 plus, right, the copper electrode. The standard reduction potential for that is 0.34, and our anode is zinc. The standard reduction potential for that is negative 0.76. So we can say 0.34 minus 0.76, right? And this comes out to plus 1.10 volts, right? So we get the same answer. We get the same answer as we did here. Here, when we're subtracting the standard reduction potential of the anode, right, that's because we're looking at the anode we have oxidation of zinc taking place, right? So we're reversing this equation. So that means we're simply subtracting the potential of the anode, right? So that minus 0.76 simply becomes plus 0.76, okay? So you can just write the two half equations and then just list their potentials and add them up to get the overall EMF of the cell, right? So you can do that, or you can simply take the standard reduction potentials of the cathode and the anode, right, and take the potential difference, right? That's how we define the EMF of the cell. It's the potential difference between the cathode and the anode, right? So simply the standard reduction potential of the cathode minus the standard reduction potential of the anode. All right, so the next one that we have here is I want to find the standard cell potential, okay, of the following cell. Okay, I have an Fe3 plus Fe2 plus half cell, okay, connected to a manganate 7 manganese 2 half cell. Okay, so an MnO4 minus Mn2 plus half cell. So we have the following half equations from the data booklet, right? We have MnO4 minus plus 8H plus 5 electrons gives us Mn2 plus and 4H2O, and this has a standard reduction potential or a standard electrode potential of positive 1.52 volts. Okay, and then the Fe3 plus Fe2 plus half cell, right? We have this guy, and this has a standard reduction potential of positive 0.77 volts. So over here, if you look at the standard reduction potentials, we can first identify that acidified manganate is a better oxidizing agent than Fe3 plus, right? The reduction of manganate ions here in acidic conditions is more favorable than the reduction of Fe3 plus ions, right? Based on the standard reduction potentials. So we can say that MnO4 minus will be our oxidizing agent. It will undergo reduction, and Fe2 plus will be the reducing agent. It will undergo oxidation. So then we can say that at the cathode, right, we have reduction take place, right? At the cathode, we're going to have reduction take place. So that will be MnO4 minus plus 8H plus 5 electrons, right, giving us Mn2 plus and 4H2O. And then at the anode, we're going to have the following reaction, right? At the anode, we're going to have oxidation take place. So Fe2 plus will undergo oxidation, right? That's our reducing agent. So we have Fe2 plus, right, forming Fe3 plus and E minus, right? Now here for this half cell, right, our electrode potential will be plus 1.52 volts, right? And then this one, we've reversed the reaction. So this one will be negative 0.77 volts, right? Negative 0.77 volts. So over here, we know that since Fe2 plus is losing electrons and MnO4 minus is accepting electrons, right? This is our negative terminal, right? The anode is this is our negative terminal, and this is our positive terminal, right? Electrons are going from the negative terminal to the positive terminal, right? From here to here, right? If we had to figure out the overall EMF of the cell, what do we have? The overall EMF of this cell, comes out to positive 0.75 volts, right? And the overall equation for this reaction, is, in order to figure out the overall equation, we have to balance the electrons, right? So here we have 5 electrons in this half equation, so we're going to have 5 electrons here. So we're going to multiply this equation by 5. Remember, this has no effect on the electrode potential. Okay, the electrode potential only changes with concentration. The number of moles do not affect the electrode potential. So we can say here that what we have is we have MnO4 minus, okay, plus 5 Fe2 plus 8H plus, right? Those are our reactants, and then the products are 5 Fe3 plus, okay, and 4 plus Mn2 plus 4H2O, right? Plus 4H2O. Plus 4H2O. So this is our overall equation. Right? This is our overall equation. And in this equation, we can clearly see that the manganate ions, right? This is our oxidizing agent, right? It undergoes reduction, and this is our reducing agent, right? And lastly, if alternatively we wanted to calculate the cell potential, we can also use the following expression. We can say that the EMF of the cell is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode, right? The standard reduction potential for the cathode is plus 1.52, right? 1.52. And the standard reduction potential for the anode, right? That's the iron 3, iron 2 half cell. The standard reduction potential is positive 0.77, right? So we have 1.52 and then minus 0.77, right? We're subtracting the standard reduction potential for the anode, right? That essentially, when we reverse this equation, right, it becomes negative 0.77. So over here we get positive 0.75 volts. Okay, so that's our answer. We have this, or you could say you have this.